lecture today. So last week we have an introduction about the first heap effect, which is caused by the water contents in the subgrade and also the temperature. And basically with the manual from MTO 90, which is one useful manual for us to design the pavement structure in Ontario. And with this manual, we can check the permeability and the capillarity potentials to identify whether one kind of the soil is first sensitive or not. And basically, with this kind of graph, you can find that if the material contains a lot of a certain portion of the fine particles, like make the soil be in a silt or silt-like materials, then it will be in it will have the severe first heap effect. But for all the other type of the soils, it will be moderate or it could be very small. And also, the manual defined a way for you to identify whether the one type of the soil is appropriate for you to design or appropriate for you to apply for the subgrade layer of one pavement design. And basically, you have to consider the percentage of the sand, the percentage of the clay, and the percentage of silt. And with these 4 values, you can then check the graph, check this triangle to identify whether it falls in the acceptable region or it's under the borderline or it's under the unacceptable region. And once it falls under the borderline or unacceptable region, then we have to consider to either apply some compaction or do some remove the those type of soils to make sure that the subgrade layer is strong enough to support the pavement structure. And we will introduce more details about how to handle this issue. And this table actually shows the first susceptibility of different type of the soils, and you can find out the soils defined by the USCS classification method. Basically, this table will categorize the soil into 4 types with different first susceptibility from negligible to low, low to medium, high, and very high. And we generally will use the percentage of the particles less than 0.075 millimeters. This is actually the percentage of the weight. And depending on these percentages, you can actually identify them into these 4 categories. For example, if the percentage is between 3 to 10, then it's defined as a very good soil for the subgrade, and the first susceptibility can be negligible. But if the percentage is higher than 15, and it's something about the silt, then it means that the first susceptibility would be very high and probably it's not appropriate for the subgrade. And this is one very simple method for you to identify whether the soil is appropriate or whether the soil is susceptible to frost. And you have to consider the percentage of the different, the grain size, larger, smaller than 0.075 millimeters, and the type of the soils. And we also have some other studies to identify the severity of the first heap. And this figure actually categorizes the first susceptibility into 6 categories, from very high, high, medium, low, very low to negligible. And this one actually.
Excuse me.
Hello. Yes.
Yes. Are you sharing your screen currently? Because I can't see. I just see you.
Oh, okay. Oh, sorry. I guess I'm sorry the sharing the screen. Just a minute. Let me try to do that. Okay, can you see now?
Yes.
Okay, sorry, I just saw that. There's too many buttons for me to press. So for this figure, I'll just jump back to the previous page. Well, this is the table to show you how you can use the percentage of the particles, the fine particles, and the type of the soil to identify the frost susceptibility into 4 degrees. And this graph is actually from the study conducted in 1974, and it will just utilize the percentage of the fine particles, and this would be the size smaller than 0.02 millimeters, and also the average rate of the heap. And I will show you how to calculate the average rate of the heap in the future slides. So with this graph, by identifying the percentage of the fine particles and also the average rate of the heap, you can find out the whether this material is frost susceptible or not. And depending on the also we have to consider the type of the soils, like it's a gravelly sand, or the clay gravel, the gravel, or the lean clay, depending on the size of the particles, the type of the soil, and also the average rate of the heap. And this is the second way for you to identify the rate of the frost heap. And I'm sorry, there will be something. Just a moment, let me try to remove another one from the, looks like the there are some pre-recorded. Okay. So the next thing that we have to consider about the frost heap, or for us to evaluate the frost heap, is like we need to calculate the depth of the frost penetration, and for the which means that how depth the pavement structure will be affected by the frost heap effect, which is also means that by the temperature and the water contents. And of course, this one is related to the local temperature and also the properties of the materials and what's the water contents in that material. In Ontario, we have a very simple equation to calculate the depth of the frost penetration, and this is actually showing the in this equation, and the depth equals to minus 12.8 plus 1.46 times the square root of f, and f is the freezing index. It is defined as the degree days below 32 degrees Fahrenheit, and which means that the degree below 0 degree Celsius is under the freezing temperature. So I just assume that you all know how to convert the temperature from Celsius to Fahrenheit. So if we have a degree in Fahrenheit, then it should minus 32 times 5 divided by 9. It will give you the degree in Celsius. You can also try to do the other way to find out the degree in Fahrenheit from Celsius. So the with this definition, you can find out the value of F, the freezing index. For example, if we say that there are 7 days at that region, there are 7 days with the temperature of 22 degrees, then F will be first we have the temperature that is 22, so we have 32 minus 22 times the number of the days times 7. It will give you the freezing index as 70. And then you can calculate the depth of the first penetration, z equal to minus 12.8 plus 1.6 times the square root of 70, and it will give you the value. Let me just quickly find out the value. Does anyone know what's the giving me value about that? Okay. Oh, I just calculate the value. So the value is 0.58 inches. Remember that the unit here is inch, and so 1 inch is 2.54 centimeters. So basically, if we are consider the first penetration in Ontario, in Hamilton area, the depth is around 2 feet to approximately, which will be approximately 0.6 meters. And in Ottawa, which is a little bit north of this, a little bit north in Ontario, the penetration is around 1.2 meters, while in the northern Ontario, while the temperature is much lower, so the penetration is could be more than 2 meters. And this figure actually shows the depth of the first penetration in North America. If you are located in the other regions of the world, you can try to check the your local organization about the pavement to see what's the first penetration. And you can see that in Canada, the penetration can be as high as 120 inches. This would be very, actually could be even larger depending on the weather, the temperatures in that region. And in the southern part of the America, such as Florida and Texas, well, they may don't have any first penetration because the temperature will always be about 0. So that's the first penetration, and it's another factor you have to consider. So basically, with the first heap effect, it will cause the we can see that the it will usually caused by the formation of the ice lanes under the ground, and those ice lanes will be formed at some of the large voids in the subgrade soil, and then it will go larger by attracting the water contents from the nearby area by the capillary raising effect and so on. And with the first heap, we will observe the loss of the strength when the ice melt during the springtime, and the strength will be reduced dramatically. And with the reduced support from the subgrade, it will make the entire pavement structure weaker, and then it will easily create the distress of the pavement, such as the longitudinal and the traverse crackings and the potholes and so on. So in order, as we know that there will be a lot of potential reasons for the first heap. So in the design, we need to think about how to minimize the impact of the first heap. The most intuitive way is like we will just remove or replace the first susceptor soils, and this is very intuitive. And then the other potential method is like because the first heap is caused by the combination of the water contents and the temperature. For one region, with the for the local region, you probably cannot control the temperature, but there's a way for you to remove the water from the pavement structure. So with that, we need to design the appropriate drainage system to reduce the water contents in the pavement structure, and also potentially we can lower the groundwater table. So in that sense, we will have less impact by the capillary raising effect. And the other way is like we can excavate the soil to the first line, which will be the line at the depth of the first penetration, and place some impervious seal so that we can prevent the impact from the first heap. And also we will put the some insulating layers to prevent the first penetration. In some region with very cold, with very low temperature, we can put some special processed aggregates to prevent the impact of the first heap to to further depths of the subgrade. And the other ways, like we can increase the size of the void with some chemicals to inhibit the soil suctions, and this will reduce the water contents in the soil. And also we can use some stabilize the first acceptor soil by eliminating the effect of the soil fines. Like we can use some cementitious bonding, such as the Portland cement, bituminous, lime, and so on. And also we can increase the pavement structure layers, like we can increase the thickness of the base or subbase layers, so that we will have less, the pavement structure will be less dependent on the subgrade. And this can also potentially reduce the impact of the first heap to the pavement structure. So with that, we have finished the introduction about the first heap and the impact of the water contents. Do you have any questions so far? Okay, if there's any question, I will go to the next one, which will continue the introduction about the highway subgrade structure. And let me just save this one first. So let's continue the introduction about the pavement structure, the subgrade structure. And this is the wish list we have to consider. And you should always keep in your mind when you design the pavement structure, especially for the consideration of the subgrade layer. So we have sufficient bearing capacity, low deformability, time-independent properties, the non-susceptible to environmental change, and a good drainage system. And the other thing for us to consider, like in addition to the consideration of the temperature, we also need to think about the moisture control at the regular temperature. And in your experiment, you will actually have already know that you will be assigned to conduct the compaction to the samples that you have to do for both CBR test and MR test. And the compaction is actually one way for us to control the moisture contents of the one type of the soil. So the usually for the compaction, there will be three purposes, like the we can compact the sample into the wethold optimal and maintain the material. It's able to help us to maintain the material uniformly along the pavement region, and also maintain the uniform moisture and the compaction. So this would be the objective for us to achieve with the compaction. And then we will have more introductions about why the compaction can achieve this the goal. And the other ways, like we can control the grading, like we will excavate a very deep cut. So we will remove the water and remove the soil from the pavement region, and then place some expensive soil only at the bottom of the field, and then cross-haul less expensive soil on the top of the subgrade, and then do the compaction to get a uniform subgrade, and then stabilize the expensive soil using, well, if the soil, the expensive the soil is very expensive, then we probably need to apply some chemicals using the cement or lime to stabilize this expensive soil to make the subgrade uniform and make it less expensive for the water contents. So with that, we can see that the compaction is actually one common method to improve or to control the moisture contents and minimize their impact to the pavement structure. So as we have the discussion a lot about the moisture contents, and in this lecture, we will need to define what is the moisture contents. So the moisture is usually actually the water that held in the space between the soil particles. So because the size of the shape of the particles in the soil is not regular, there must exist some space or air voids between those particles. And if there's some space in between, with certain waters, either from the rainfalls or from the nature waters, they will have some waters held in these small voids, and this is defined as the soil moisture. And we can actually estimate the moisture contents by using the oven, which is what you are doing in the lab experiment. So first of all, you have to select the sample and weigh them with the certain moisture contents, and that will be the white weight. And then you have to put the sample in the oven at 105 degrees for 1 day. And of course, that depends on the temperature of the oven. In our lab, we don't need to wait for so long. If you put the sample in the oven for long enough time, and then all the moistures will be removed from the sample. And after that, you will just wait the dry sample, and then you will have two values: the white weight and the dry weight. Then the moisture content is defined as the percentage between the white weight and the dry weight. It's defined as wet weight minus dry weight divided by dry weight times 100. So this is actually the percentage of the water in the sample. And of course, the value could be very small and could be very high, depending on the type of the soils. So by knowing the definition of the moisture, we can then identify the impact of the compaction to the moisture contents. For the soil compaction, we actually in the pavement design, we actually have some standard protocols. But basically, all those compactions will actually put the soil in a dense state. So they will apply some weight to the soil and make the soil increase the density of the soil and reduce the air void between the particles. And sometimes if the water content is high enough, the water from the sample could be from the soil can be squeezed out, and this will reduce the water content a little bit. The soil compaction is actually a little bit different from the consolidation. Usually for the compaction, we will have a repeated load applied to the surface, or we will have the rollers have to conduct the kneading process along the surface of the soil. But in the consolidation, the water will just be squeezed out based on some static load. So they have certain difference. And usually with the compaction, we can observe some distinct changes about the soil. So by applying the compaction, the strength and the bearing capacity of the soil can be increased, and which means that stiffness of the soil will be increased. and also is able to decrease the amount of the undesirable settlements of the structure and increase the stability of the slope of pavement. So you basically can observe this effect in these three pictures. So for the orange one is actually shows the soil without any compaction, and the blue one will be the one with the compaction. And you can see that usually when you increase the apply the compaction, the surface will be the soil will be, the stiffness of the soil will be larger, and it will be less likely to have the fatigue, cracking, or the rotting along the wheel paths. So the surface of the road will be smoother and it can last for a longer time. And the other things like with the compaction, the soil will have a higher resistance to deformation and higher resistance to the force damage. So it means that if the soil is loose without any compaction, it can easily hold a lot of water in between, and then the stiffness of that soil would be small, and then the shape of the shape of the soil can be easily changed by the repeated loads, which you see that the deformation would be very large. And of course, it's able to increase the stability and decrease the permeability, and which means that the pavement structure can last for a longer time without a large deformation. So this would be the benefit for us to introduce the compaction. And in general, with the soil compaction, we can also increase the shear strength, increase the bearing capacity, the slope stability, and pavement strength. Also, it can reduce the permeability, so the water from the surface of pavement will not be easily forced behind the subgrade, or they will not easily be held in the soil. And it can reduce the compressibility, so it's the stiffness of that material, the soil is larger. And another good thing about the compaction is that I can control the swelling and the shrinkage effect. So it will be less sensitive to the water contents and the also the impact of the temperature. And these two figures actually shows the typical effect of the soil compaction. So generally, by applying the compaction, we will only reduce the volume of the air voids, which means that we will squeeze the air out of the soil, but we don't decrease the volume of the solids or the soil grains. So you can actually see these two figures, like from the in the figure in the left, you can see that by the compaction, even with those irregular shapes of the particles, you will see that those the solids were all compacted together, and the space in between, and the air walls in between will be reduced dramatically. So we will actually reduce the volume of the whole sample or the entire soil, but the reductions in the volume is only caused by the changes of the air voids. On the right, you can also see the similar effect, like those for those particles, they will be compacted with very dense to a very small region, and they will be very dense, and the air voids there will be very small. So with that, you can actually see that without a compaction, you will observe a certain amount of the air voids, a certain amount of the water and the solids for one type of the soil. But after the compaction, the amount of the water, the amount of the solids, and the amount of the air, the amount of the water and the solids will be the same, but the volume of the air is reduced dramatically. So now I will just ask you one question. So do you think at this kind of process, the compaction, is the moisture contents will the moisture contents be increased or decreased? What is going to happen to the moisture contents? Do you have any ideas about it? I get an answer about increase, and any other thought? Okay. Yes, I think Thierry get the right answer. So basically, if you do the compaction at most of the situation, you will not change the moisture contents. Only under some real situation, when you squeeze the water out of the sample, then you will reduce the moisture contents. So this can be calculated by some assumptions about the mass of each content. Say that we have the mass of the water, the mass of the soil, and the mass of the air. So basically, for the air, the mass would be 0, and after the compaction, you have you still have the different mass of the air, but the weight is 0. And they have the mass of the water. The water would be the same, and the mass of the solids is still the for the mass of the water and the solids, they keep the same. But if we go to check the definition of the moisture contents, it will actually be the wet weight. The wet weight would be the mass of the water plus the mass of the solids. And the dry weight will be the weight of the soil by removing all the water. So you have the dry weight as MS. So the for the moisture contents, will be the wet weight minus the dry weight divided by dry weight times 100. So in this equation, you can see that the wet weight will keep the same before and after. They're all mw plus ms, and the dry weight is also ms. It's always the same. So you always have the same. You always have the same value of the moisture content. So no change. And there will be some other. You might be a little bit confused about it. There will be some other measurements, some other variables to measure the property of the soil with respect to the volumes, and we will actually have some introductions about those variables in the third tutorial session, and in that tutorial session we will introduce those concepts, and it will be highly related to the design of advanced pavement material, which is called the Subgrade, and we will learn how to calculate those variables in the future slides. Okay, and then we can then go to check the impact of the compaction to the get a more detailed information about the compaction to the water contents and also the property of the soil. So here we have the in this figure you can actually see the relationship between the dry unit weight with respect to the water contents. Here the dry unit weight is just the density of the soil. It's not the dry weight, it's just the density of the soil. And each line will represent the relationship under one compaction level. Compaction level 1, compaction level 2. So basically, under the fixed compaction level, there exists a concave relationship between the density and the water contents. Do you have any ideas why we have this kind of concave relationship? Can you imagine why we can have this relationship? Okay, maybe I can give you a very simple explanation about it. So assuming that we have the sample, this is the sample, and in this sample, the soil, we have the set of the a lot of particles in between, and of course we have some waters. We have some waters there, and under one fixed compaction level, then the this would be the structure of the soil, including the particles, the air, voids, and the water. By increasing the water contents, which means that you're gonna assuming that at the one water contents we have the weight, the mass of this one as 1. By increasing the water contents, you will have more water filled to this small air voids, and this means that you will have another weight of the sample. Definitely by increasing the amount of the water in this sample, so the weight will be larger. And after you pass on the value, once you will see that almost all the voids will be filled with the water, and then you will have the you will observe the swelling effect of the water contents, like you soak the sample in the water. The volume of the sample will increase. So with that, even though you have you have more water contents in between, but as the volume increased, so for the dry unit weight, you will see that even though you increase the weight, the total weight of this soil, but you also increase the volume, and eventually we'll find that this one will actually make the say that this is the density, and we have density 1, density 2. So we have density 1 smaller than density 2, but density 2 could be larger than density 3. So that's the reason you observe the increased trend at the low moisture contents and decreasing trend at the high water contents. So at the point where we will observe the highest density or the dry unit weight, then we will define this point. We will define this point with the highest density as the optimal moisture contents, and this is actually optimal moisture contents for the compaction level 1. By increasing the compaction level, like from 1 to 2, by applying higher weight for the compaction, you will observe the changes of the relationship between the dry density and the dry unit weight and moisture contents. Basically, with this one, by the increasing the compaction level, you will see that the density will be larger. You will also observe that the shift of the optimal moisture contents, basically the optimal moisture contents will be smaller. It will shift to left a little bit. This also indicates that the sample, the soil with higher compaction level will have less permeability to hold the water. So that's the impact of the compaction, and we have the compaction curve. And if we try to do the compaction, apply different compaction levels for the same type of the soil, we will observe multiple lines, multiple relationship between the dry unit weight and the moisture contents. By applying the points at the optimal moisture contents, you can draw the curve, and this curve is called the line of the optimals. And this line of the optimals is actually the optimal line caused by the different compaction levels. And in this curve, you will also observe another line, which is called the zero air void line. We also define this one as the saturation line. This is actually in a theoretical line. It does not exist in reality. This line indicates that it's based on the assumption that there's no air void in the sample. So it means that for the sample of the soil, it either contains the air voids, either contains the solids, or it contains some water. So there's no air voids in between. And with that, you will have the line to represent the relationship between the density, the dry unit weight, and the water contents. But obviously, with a higher water contents, the density would be smaller. That's actually based on the assumption that the density of the solids is always higher than the water. So with more water contents, the density of the soil would be smaller. And this is just a theoretical line. And in reality, we cannot find this line because in reality, no matter how you compact the soil, there always exists some air voids in between. And you will also find that this line or the realistic line, even under different compactions and different water contents, they will never interact with the saturation line. It just shows the boundary for the relationship between density and water contents. So with that, we can make a quick summary about the effect of the moisture and the effect of the moisture and the compaction level. So by applying the compaction, we need to consider the water contents. They have a significant impact to each other, and also for the compaction level, it's actually determined by the amount of the compactions, like how many drops of the weight you actually applied to the sample, and what kind of weight of the what kind of weight you apply to the sample, and so on. And also the effect of the compaction is related to the type of the soil and the amount of the compaction energies, how many times you apply the compaction, and the method for you to conduct the compaction, and the thickness of the layer and the saturation line. The saturation line will actually have a significant impact about how the line of the shape is how the line of the shape looks like, and what kind of the boundaries for the line of the optimal. So in reality, we have multiple ways to conduct the compaction. In the lab, we will use two different methods. Usually we will use actually in our class, we will only consider two different methods. For the coarse-grained soil, we will use the vibrating hammers. And this is actually conducted in the resilient modulus test. And for the CBR test, we actually use the falling weight and the hammers. this is you need to apply certain amount of the drops to compact the sample. And of course, for some other lab experiment, we can use the kneading compactors or the static loading and press, but these are less common. In the field, for the coarse grained soil, the vibration is very common. So you can use the hand operated vibration place, which is the similar to the one we use in our lab, and you can use the motorized vibratory rollers and the rubber-type equipments and so on. And for the fine-grained soil in the field, we're gonna use a kneading method. We can use some hand-operated tempers, the sheep foot rollers, or the rubber-type rollers, and so on. So all these methods are applied in the lab and the field projects. So for the basically in our lab, there will be also for the pavement design projects, there will be some standard protocols for us to conduct the compaction. You can actually check this method for your lab experiment and see whether you are doing the experiment correctly or not. So usually for a sample, we will compact the soil sample into a mold with 3 to 5 equal layers. In our lab, it's of course it's set as 5 layers, but depending on the what kind of compaction levels you conduct it. So what I suggest for your analysis of the lab report, please consider your compaction efforts when you are preparing the sample. And for each layer, you will receive 25 blows of the hammer with the standard weight. And usually the weight is around 25 kilogram. And the energy supply in this test will be around 595 kilojoule per cubic meter. And that's actually depends on the standard mode you applied. Well, for the standard mode, the volume is 1,000 cubic centimeters, and the height of the hammer for the drop is around 300 millimeters. So you can use those information to conduct a standard proctor of the compaction. I think I almost run out of time for the lecture today. So with that, I'm going to stop here. Do you have any questions so far? And do you have any specific concerns about the class? You can just bring your questions at any time. Okay, if you don't have any question, then that will be all about the lecture today. And just let us know if you have any questions about your homework or the lab report, and we are very happy to help you after class. Okay, good. Thank you very much for your time. I guess that's all about the lecture today, and I will see you on Wednesday.